Before we can understand how to design large-scale distributed systems, we have to first understand how a computer is designed, at least at the high level. We'll be going over the main components of a computer, at least from a software perspective, and how they work together to execute the code that we write. Let's first start with our disk. At least that's one way to refer to it. You could also refer to it as the storage, or maybe the hard drive, or HDD, which stands for hard disk drive. Nowadays, it's more common that you would be using an SSD rather than an HDD just because they're generally faster. But the idea behind this component is that this is going to store all of our data and it's going to do so persistently. What that means is that even if our computer restarts or if our computer crashes while we're executing some code or while it's running some program, the stuff that we store inside of our disk is going to be persisted. That means, for example, if we store some file in our disk, but then our computer crashes, it's okay because the file was saved to the disk. Now, how much information can it store? Well, it's usually measured in terms of hundreds of gigabytes, or more commonly in terms of terabytes. And just to quickly review, remember a byte is nothing more than 8 bits, and each bit can either store a 0 or a 1. And we can use these bits and these bytes to represent information. So this could, for example, be the character A or the character B. And as we kind of combine all these bytes and bits together, we can end up with some very sophisticated software and programs that run like games and videos and things like that. So when we say that a disk might have, for example, 1 terabyte of storage, well, that T is actually 10 to the power of 12. So this could have a trillion bytes inside of it. So 10 to the power of 12, I think, is a trillion. So that's quite a lot. 1 gigabyte is 10 to the power of 9. So that is actually also a lot of storage. This might be a USB drive, for example, that you're using for storage. Usually disks have a lot more than just a single gigabyte. Now we also have our memory, aka our RAM, which stands for random access memory. And this is also used for storing information, though it's typically a lot smaller than our disk. So for example, our RAM might contain something like 2 gigabytes or maybe 4 or 8 or 16 or even 32 gigabytes, and it can go higher than that, but typically it's a lot less than our disk storage, and that's because RAM is typically more expensive in terms of money, in terms of how much we have to pay for this resource. But the benefit is that it's a lot cheaper in another way in terms of resources. If we're going to be writing data to our RAM, so for example, if we wanted to write a megabyte of data to our RAM, the amount of time it would take would be measured in terms of microseconds. So this is a Greek letter, which basically stands for micro. And micro basically means 10 to the power of negative 6, which is 1 divided by 10 to the power of 6. So a microsecond is a fraction of a second. It's 1/1,000,000th of a second, or a second divided by a million. So in general, reading and writing from RAM is measured in terms of microseconds. We're not going to get super precise because you don't have to memorize exactly how quick it is. But what I'm trying to get across is that reading and writing from RAM is a lot faster than reading and writing from disk. So while we can't store as much information in RAM as we can in disk, because at least that's generally the case, the benefit is that RAM is quite a lot faster than disk. Reading and writing from disk is typically measured in terms of milliseconds. A millisecond is 10 to the power of negative 3, aka 1 divided by 10 to the power of 3. So a millisecond is actually a lot bigger than a microsecond. So when we say RAM is a lot faster than disk, we're not talking 10% faster or 50% faster. We're talking at least 10 times faster, or sometimes 100 times faster, or even 1,000 times faster. It's an order of magnitude faster. Now, maybe if you're using a really, really good SSD, maybe that's not going to be the case, but this is generally what's true. You don't have to remember the exact decimal. As software engineers, this is just something that we generally believe to be true. RAM is a lot faster than disk, and it's usually the case. Now, how exactly do we write data to our disk or to our RAM, and how exactly do we read or retrieve data from our RAM or from our disk? What if we even want to communicate between the RAM and the disk? These components can't directly talk with each other. That's why we have to introduce another component, which is our CPU. CPU stands for Central Processing Unit. It's essentially the brain of our computer. And what it's capable of doing can be quite complicated, so we're going to simplify it. The main things that the CPU is capable of is writing information to RAM or writing information to disk. And when we talked about the time that it takes to write from RAM and to write to disk, this is what we meant. How much time it takes the CPU to perform these operations. The CPU can also read from RAM and can also read from the disk. Now, what exactly is the CPU going to do with that data once it reads and writes it? Well, the CPU is going to execute code. So we can assume that the code that we wrote is written somewhere in memory. Now, of course, the code that we write with English characters is going to be compiled down into instructions that the CPU can actually interpret. We're not going to go into the details. We know it can get quite complicated, especially when you're talking about zeros and ones, but we know that that's essentially how everything is represented in terms of zeros and ones, but it can have different abstractions around it. Like the code that we write is going to be written in English text typically, but it's going to get compiled down into instructions that the CPU can interpret. It's all represented in terms of zeros and ones, but it represents different information. So the CPU is going to be reading our code so that it can execute that code, but it's also going to be reading and writing from RAM for a different reason. There's going to be some data stored in the RAM that's not our code itself. So we could have other data stored, somewhere in RAM. This isn't the most accurate depiction, but the main idea I'm getting across is you could have some code, have some, pseudocode over here that is declaring some variable and then maybe looping through that. Like maybe we declare an array and then we loop through that array. So those instructions are code, and that's what is going to be stored over here. But the variables that we declare, so in that code, we declared some variable, right? Some array. So that's going to be stored in the data portion of our RAM. So the CPU is not only reading the code that we may have written, but it's also could be writing to some data and manipulating that in some way. And the CPU does this actually just by reading, writing, and performing computations within the CPU. So all computations are done in the CPU. That's actually all a CPU really knows how to do, perform computation. I'm talking about arithmetic here, add, subtract, and those type of operations, because remember, everything is just zeros and ones, but we can use this to represent very complicated things. In our code, we might be programming some type of video game, and this can all be done through a CPU. Now, while the read and writes from RAM are pretty quick in terms of microseconds, what if we want to go even faster? Well, actually, CPUs have another component called the cache. It's typically a lot smaller than disk and a lot smaller than RAM as well. It's typically measured in terms of megabytes. This is actually a component that's not separate from our CPU. It actually belongs to the CPU itself. And it's used to speed up read and write operations from RAM. And this is possible because reading and writing from the cache is actually on the scale of nanoseconds, which is 10 to the power of -9, which is basically 1/1000th of a second. So it's a very small fraction of a time, even smaller than a microsecond. But of course, the downside is that it stores a lot less data in terms of megabytes, whereas RAM is typically in terms of gigabytes and disk is typically in terms of terabytes. And the cache is mainly used as a substitution for the RAM. So what the CPU will do is it'll take a subset of the RAM, some portion or maybe multiple portions that can fit within our cache, and we want to choose these portions intelligently, at least the computer does. So the CPU will typically choose portions of the RAM that we're writing to or reading from very frequently. Because we have a limited amount of space in our cache, if we find that we're reading this portion of RAM a lot, we can go ahead and throw it in our cache because we know we're going to have to be doing this operation frequently. So why not have it in our cache so that we can perform it, 10 or 100 times or maybe even 1,000 times faster. This will speed up things a lot. So technically it's not necessary that we need a cache, but practically it can make things go a lot faster, even though caches are expensive in terms of money. So we can't have huge caches. Even a small cache like this will improve the performance of our entire system by a lot. So if the CPU wants to read some data from RAM, it can first check if that data is in our cache. If that data is not there, then we will perform the more expensive operation, which is actually reading from RAM. But maybe if we read some data, we'll go ahead and throw it into our cache so that next time we have to read it, we can directly go to the cache and it will be faster. So if we read from our cache and we do find the data there, then we don't have to perform that operation where we have to read from our RAM, and that will go a lot faster. Now, the downside of RAM and cache is that it's not persistent data. That means if we throw information in our cache or in our RAM, and maybe our computer crashes or we restart it, we are not guaranteed that the same information that we stored there is going to be persisted. So if you're writing an essay and that essay is stored into RAM and your computer crashes, then you're going to lose all of your progress. You want to make sure that your essay is written to disk so that if the computer crashes, it's still there somewhere, and then we can go ahead and read it, and then you can basically start where you left off in writing that essay. So this is a general computer architecture, at least at the high level. Of course, CPUs are a lot more complicated. They have registers, and of course there are GPUs as well. But as software engineers, this is generally what we have to worry about. And believe it or not, there's actually a lot of parallels from just what we talked about here when it comes to designing a distributed system as well. There are a lot of parallels between the two. And we can actually take an individual computer like this and use it to solve very big problems when we combine multiple computers together. So when it comes to designing distributed systems, a computer like this is the building block that we have. In fact, we need to combine multiple machines in order to solve those big problems because an individual computer actually has a lot of limitations. Now, if you need more storage, well, why not just get a bigger disk or get multiple disks? Okay, fine. If you have really, really large programs, you could also get more RAM or a bigger cache, and you can do these things, but they all do have some type of hardware limitation behind them, and the biggest hardware limitation comes from our CPU. How fast we execute our code is limited by our CPU. At least that's one of the limitations. You've almost certainly heard of Moore's Law. It's named after Gordon Moore, who is one of the co-founders of Intel, so he definitely knew what he was talking about. And it's not really a law, it was mainly an observation by him, which was that over time, the number of transistors inside of a CPU doubles every 2 years. And the cost is cut in half every 2 years, but we're mainly going to be focusing on the number of transistors, which basically in this case is going to be a proxy for the speed of that CPU. So we can essentially assume that the speed of our CPU is going to double every 2 years. So we can assume that the speed of our CPUs is going to increase exponentially. And typically this is scaled exponentially. So you'll see this drawn more oftenly as this, where the slope of our line is linear because the scale of our chart is exponential. So this doesn't actually mean the speed is growing linearly, it's growing exponentially. But in reality, we've seen that CPU speeds are actually beginning to plateau. Roughly in the last 10 years, the speed has slowed down. So we can't infinitely scale a single CPU. That's the point I'm making. So we are limited, and this is just one limitation of an individual computer. We've actually had distributed systems well beyond the point that we reached, the limitations behind a single CPU. But the point is that we can solve bigger problems when we combine multiple computers together because individual computers do have limitations. Moore's Law is beginning to break, and there are other benefits of distributed systems that we're going to talk about later in the course, including what a distributed system is in the first place. I know I haven't talked about that just yet.